Welcome to this new activity, which is about computing partial derivatives of first order and second order. So you have to keep in mind that we are dealing with multivariable functions. So when you are differentiating a function with respect to a variable, the remaining variables will be considered as constants, or the other variables will be considered as constants. We have two first partial derivatives of first order if you have two inputs, fx and fy. If we move to the second derivative, we have four second order partial derivatives. So let's compute the 6 quantities for each of the given functions. So let's start with the first one. The polynomial function f of x and y equals 3x squared y plus 6x squared plus 2y cubed. So we will start by computing the first order partial derivatives. It means the partial derivative with respect to x, fx of x and y, and the partial derivative with respect to y, fy of x and y. When you compute the partial derivative with respect to x, you consider the y as constant. So let's highlight the expressions depending on x to be able to compute this partial derivative. The x appears in the x squared here and in the x squared here. Okay? So the derivative of 3x squared y with respect to x will give 3 times 2x times y, since the derivative of x squared is 2x. So the derivative with respect to x of x squared is 2x times 3 times y, which gives 6xy. Now, for the second quantity, you have x squared, its derivative is 2x multiplied by 6, it gives plus 12x. And the last term has no x inside, so it's not dependent on x. It's considered as constant, and its derivative with respect to x is simply 0. Okay? So your partial derivative with respect to x is 6xy plus 12x. Now let's move to the partial derivative with respect to y. And here we're going to consider the x as a constant and the y as a variable. So let's highlight the y in our expression. The y appears here, and it also appears in the y cubed. So we're going to focus on these two quantities and make their partial derivatives with respect to y. For the first term, the derivative of y with respect to y is 1. 1 multiplied by 3x squared, it gives 3x squared. Plus, for the second quantity, there is no y, so it gives 0. Plus, and in the third term here, we have y cubed. Its derivative with respect to y is 3y squared. Multiplied by 2, it gives 6y squared. Now we are done with the first order partial derivatives. We're going to move to the second order partial derivatives. And as I said, you have 4 second order partial derivatives, which are fxx. It means you're going to make the derivative with respect to x twice, okay, of x and y. You have also the fxy. It means you're going to first apply the partial derivative with respect to x and then compute its partial derivative with respect to y. So let's do this. We have already fx, which is computed here. We're going to make its derivative, its partial derivative with respect to x. Again, here you can use a highlighter to highlight the x's in the expression, since you are making the derivative with respect to x again. Okay, so the x appears here and here. The corresponding derivative will be 6 times 1, since the derivative of x with respect to x is 1. 6 times 1 times y, so 6y, plus obviously 12, since the derivative of x with respect to x is 1. Now, we're gonna make the derivative of the same quantity, but this time with respect to y, since we are asked to compute fxy. So I will highlight the y inside, and the y appears only here. Its derivative with respect to y is 1, so you're going to obtain 6x, and there is no y in the second term, which gives 0. Now let's move to the second derivatives. derived from fy, so we're going to compute fy first, and then compute fyx of x and y. Okay? Now, fyy, it means we're going to consider fy and make the derivative with respect to y. Okay? The y appears only in the 6y squared, and the derivative of y squared is 2y times 6, it gives 12y, and the first term gives 0 since there is no y inside. So it gives 12y for fyy, and for fyx, you're going to compute the derivative of fy with respect to x. There is no x in the second term, so we don't consider it, and we have here x squared, which gives 2x times 3, it means 6x. Okay? Of course, you can check that the mixed second order partial derivatives, fxy and fyx, are equal, and it's always the same when you have independent y. Okay? So 6x equals 6x. This is a way to check that your work is correct. Now, let's move to the second example, in which we have x squared multiplied by ln of y. It's no longer a polynomial function, but it's a product of a polynomial function of x and a logarithmic function of y. Now, again, we're going to consider fx and fy first. So let's compute what is the first order partial derivative with respect to x, the first order partial derivative with respect to y. Now, for fx, it's simple. The derivative of x squared with respect to x is 2x times ln of y. And if we move to the partial derivative with respect to y, we have x squared, which is a constant, and the derivative of ln of y with respect to y is 1 over y. So the result is x squared multiplied by 1 over y, or simply x squared over y. Now let's move to the second order partial derivatives. We're going to compute fxx first. Here again, it's very simple, since the derivative of 2x with respect to x is 2 times y. Now, we're going to compute fxy of x and y. Now, we are making the derivative of this quantity with respect to y. It means that it's 2x times the derivative of ln of y with respect to y, which is 1 over y. It's 2x times 1 over y, it's 2x over y. Now, let's move to the other side. So, we're going to compute fyy, which is it. Now, if you look to this function, you see the y in the denominator. So the function of y in this expression is 1 over y, since the x squared is considered as a constant. And you know that the derivative of 1 over y with respect to y is negative 1 over y squared. Multiplied by x squared, the result will be negative x squared over y squared. Now let's move to fyx. We expect to find the same quantity as fxy, so we're going to find this, but let's check. Now, if you look to this quantity and make its derivative with respect to x, it gives simply 2x over y, since the only expression in x is the x squared, its derivative is 2x over y. And we check that we have the same result. Next one. This is a logarithm of a function of x and y. It's a logarithm of a polynomial function of x and y. Let's do it. First, compute fx. Here we're going to use the chain rule. Since it's a logarithm of a function, we're going to use the single variable chain rule, which is the derivative of ln of u, if a u is a function of x or y, is u prime over u. Remember this rule, the derivative of ln of u is u prime over u, but instead of u prime, you're going to use the partial derivatives with respect to the corresponding variable. Here we're going to compute fx, so we're going to make the partial derivative of x squared plus y. It means the u function inside the ln over u. The derivative of x squared plus y with respect to x is 2x over the u, which is x squared plus y. It's as simple as that. Now, if you move to fy, we're going to use the same rule, but this time you're going to make the derivative of x squared plus y with respect to y, which is 1, because it's 0 plus the derivative of y with respect to y, which is 1. So it's 1 over u, which is x squared plus y. Now we'll move to the second derivatives. And here I will give you some tips to get the result correctly and quickly. Now, I will compute fxx first. So, look to fx and compute its derivative with respect to x. From an x point of view, this function here can be seen as a quotient of two functions of x. So, we're going to use the quotient rule to compute the derivative of this function with respect to x. So, let's start. Here, it's 2 times x squared plus y. This is the first part of the quotient rule, minus the derivative of x squared plus y with respect to x, which is 2x, times the numerator, which is 2x, over x squared plus y squared. So it's u prime v minus v prime u over v squared. So, of course, you can simplify this expression. It's 2x squared plus 2y minus 4x squared. So, the result will be 2y minus 2x squared over x squared plus y squared. Now, let's move to fxy. Of x and y. Now, we're going to look to this function and make its derivative with respect to y. But this time, from a y point of view, it's not a quotient of two functions of y. It's just the inverse of a polynomial of y. It means that what's on the numerator is no longer a function of y. It's considered as a constant. So let's write this function differently just to make sure to make it in the easiest way. So let's write 2x times x squared plus y to the power of -1, and we don't need to use the quotient rule since the 2x here is considered as a constant. So let's write it. It's 2x, and the derivative of x squared plus y to the power of -1 is times -1. The derivative of what's inside with respect to y is 1, so we don't need to write, and then it's times x squared plus y to the power of -2, and here we use the power rule. Okay, so you don't need to make this derivative using the quotient rule. You can do it using the power rule. So if you want to write it in a more familiar form, we can write it as -2x over x squared plus y to the power of 2. Okay. Now, let's move to the other side. We have fy. We're going to compute first fy y of x and y. So, again here, you can use the form x squared plus y to the power of -1 to get your derivative with respect to y. You don't need to use the quotient rule. So, apply the power rule to this function with respect to y. Yes, -1, negative sign. The derivative of what's inside with respect to y is 1, so we don't need to write it, and then x squared plus y to the power of -2, which can be written as -1 over x squared plus y to the power of 2. Now, we move to fyx. Again, here you don't need to use the quotient rule. Use this form with the power rule. So it gives negative, the negative 1. Then the derivative of what's inside, but this time with respect to x. And the derivative of what's inside here with respect to x is 2x, okay, times x squared plus y to the power of n minus 1. It means minus 1 minus 1, which is minus 2. Of course, we can write it as negative 2x over x squared plus y to the power of 2. And we can check that we obtain the same result for fxy and fyx. You can check by yourself that we have the same one. Next and last example, an exponential example which involves x and y. So let's start with computing fx. Remember that the derivative of exponential u is u prime exponential u. But instead of u prime, consider the partial derivative. So the question here, what is the derivative of this function u with respect to x? The answer is simple. You have only an expression on x here, which is x. Its derivative is 1 multiplied by y squared, so its derivative is y squared. So the derivative of this function with respect to x is y squared multiplied by exponential u. It means exponential x y squared. Now let's move to fy. Again, here we're going to use the exponential rule for the derivative, and here we're going to try to find the derivative of this expression with respect to y. We already did it in the previous examples. It's just 2y times x, or 2xy. So it's 2xy multiplied by exponential xy squared. Okay? Now, let's move to the second part, second partial derivatives, second order partial derivatives. Let's start with fxx. Again, from an x point of view, this function is not a product of two functions of x, but it's a constant multiplied by a function of x. So let's write the constant first. And the question now, what is the derivative of exponential xy squared with respect to x? We already did it in the first partial derivative. It gives y squared exponential xy squared. So the result is y to the power of 4 exponential xy squared. Now let's move to fxy. Now, if you look to this expression from a y point of view, so if you place the y here and look to this expression, it's not a constant times an exponential. No, it's a function of y, which is y squared, times another function of y, which is exponential xy squared. So you have to apply the product rule to get the derivative. Okay? So from a y point of view, this is a product, so we're going to apply the product rule, and the product rule will give 2y, which is the derivative of y squared, times exponential xy squared, plus y squared, and here you're going to compute the derivative of exponential xy squared with respect to y, which is 2xy exponential xy squared. Okay? Of course, you can write it in simplified form. You can write it as, we can put the 2y exponential xy squared in factor here, so 2y exponential xy squared as the factor of what? As the factor of 1, plus what remains here is 2, so plus xy squared. Okay? Now let's move to the other side. So we're going to compute fyy, which is the partial derivative with respect to y of fy, which is here. So it's a product of two functions of y. The first derivative gives 2x times exponential xy squared plus 2xy times the derivative of exponential xy squared with respect to y, which is 2xy exponential xy squared. So again, times 2xy exponential xy squared. Of course, we can write it as 2x exponential xy squared plus 2xy squared exponential xy squared. Now let's move to the last quantity to compute, which is fyx. So we're going to make the derivative of fy here with respect to x. Again, here it's a product of two functions of x. So the first derivative of 2xy with respect to x gives 2y multiplied by exponential xy squared. We are applying the product rule plus 2xy times the derivative of exponential xy squared with respect to x. It gives y squared exponential xy squared. So here we can, of course, write it as, we can check that it's the same quantity here, okay? And we can write it as 2y exponential xy squared times 1 plus, so plus xy squared. Of course, we check that it's equal to fxy, okay? That's it. We are done with this activity. See you in the next videos.